Oh, you have that. We have the same make. All once they we're going for it.
Actually.
That is their sole purpose.
Oh, being serious.
And then they go to right there. Where is the
Play something. Play something. For 30 seconds.
Exactly. It's just.
Actually, there's a.
Okay, guys, page 13.
No, we should.
We got started with example 5, but we didn't finish it. Is that correct?
Yeah.
Okay. All right. So let's continue working on example 5 and talk through the rest of this problem. So the first thing is that with cone problems, there's always going to be this additional basically too many variables within the problem. And we would like to pare it down to 2 variables on the right side. We can't do anything with volume, but maybe I can get a way to replace R in terms of H or H in terms of R. So here we're just trying to figure out, okay, if I can build a relationship between radius and height of a cone, then I can replace one with the other. And then once this is down to 1 variable, I can just take the derivative with respect to time and work towards solving for whatever I'm looking for. Okay, so we talked about how we can take this, understanding this is really a triangle within a triangle, that we have a similar right triangle relationship here. And I can say R and H are moving, these are also cones, but these are cones shaped, this is the water that's shaped by the container, so it looks like a cone, but it's ever changing, right? So R and H is always changing because water is getting poured in. So we can create, though, a relationship is that at any moment in time, the radius is to the height. So the radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. Okay. Information that I can gather from the problem here is that water is flowing to the tank at a rate of 10 cubic feet per minute. So I know that dV dt is a positive 10. I know I'm looking for the rate of change of the depth of water, so I'm looking for dH dt when the water is 8 feet deep, when H is 8. But put a star next to this because we're not going to use this until the appropriate time. Okay? So do not touch or do not use until the very end. We're going to be tempted to want to use this a little too early. And it makes sense because, well, there's an H here, so why not just replace H with 8? And the reason is because if we replace 8 in for H, that means we're saying that as water is getting poured in, the height of the water level is going to stay 8 forever, which we know is not true, right? We know the 5 and the 12, those are set in stone. Those are not going to change, but this H is still changing. So we want to hold on to this H variable until after the derivative. Then we can plug in once we have something that's locked in terms of the derivative, at a point. But at this stage, we need to hold on to this variable. Okay. And the next decision to make is, how do I know which variable to solve for? Do I solve for R? Do I solve for H? And either one is actually okay. But there's one that's going to be a little faster, and that faster way is looking to see some context clues here, right? Everything that's given to me is in terms of H. So it just makes sense if I can just get rid of R, because if this is in terms of h, then these will naturally show up on its own. Okay, so what I want to do is I want to solve for r, I want to replace r, and I want to get this right side in terms of h because I want these to pop up within my derivative process. Okay, so I'm going to cross multiply here. I'm going to solve for r here. So 12r equals 5h.
But how do you know which process is going to be easier? Like, would just going to be like slightly less messy?
Yeah, slightly less messy. And I'll walk you through if you went down the wrong path or the longer path, it's easier to switch back to where you're looking for at the end. Okay, but for now, just see that, okay, the context clues is that, okay, if I see a bunch of h's and I have all these things, I'm looking for something in terms of h, it just makes it more straightforward to do things in terms of h. But we can also do this in terms of r, but I'll show you that process. All right, so I want to solve for r because I want to replace r. So if I solve for r is equal to 5h over 12. Okay, so now I'm going to make a substitution, right? The goal in mind right now is how can I get that right side in terms of just one variable? And we decided that h was what we're going to target, which means that r, we're going to replace r with something in terms of h. We have that relationship here. So I'm going to make that substitution. So v is equal to I over 3 r squared h. Okay, very good so far. So one thing is taken care of. At least we got everything in terms of h. That's a start. But your derivative should be easy. Okay, so we don't want to do a derivative here. That's too complicated, having to go through a product and chain when we can simply rely on power rules. We just do a little bit more cleanup, then the only thing that we need is power rules. So I'm going to distribute that squared through each of the terms inside the parentheses. Continue cleaning up. The 25, the pi, the 3, and 144 can all be pushed out in front, and I can also merge the h's together, make it h cubed. Okay, so it's a lot easier finding the derivative here than it is over here. There's no need to rely on such complex rules when we have something easy like power rule that we can use. All right, everybody good so far? All right, so the right side is a lot cleaner than before. We've gotten rid of one variable, and we should be able to get these variables to show up so that we can actually use them. All right, so let's find the derivative now. V becomes. This is just one messy coefficient. It's not going to go anywhere. H cubed becomes 3h squared. Anything else?
H.
So now that we have the derivative done, now everything is fair game. Now we can start putting information in, right? So now we got to the point where we can involve the h. But not until the derivative shows up and we're ready to start plugging in and finding values for our final answer do we want to involve that 8. Okay, so now we can involve the values that we see. So dv dt is 10, so we have a place for that. H is 8, we have a place for that. And then we're simply looking for dh dt. You will get to use a calculator, but I still want the answer in terms of exact values. So do not plug pi into the calculator. Treat pi like a variable in the sense that you're just going to, wherever it ends up, just make sure you hold on to that pi. So here, if I multiply this out, I would get 25 times 3 times 64, but don't create a decimal with that pi. I just leave pi out of the calculator. So if I multiply all that together, I get 4,800. Okay, I want to solve for DHDT. This is a fraction here. Dividing by a fraction is easier to think in terms of multiplying by the reciprocal, so I'll do that. And then here, 4320 divided by 4,800. I can reduce that in the calculator. Now notice where's pi in my answer here? Denominator. So it needs to stay in the denominator. If you make it float up to the top, that's a different number, right? So that's the wrong answer. If sometimes pi is in the numerator, that's fine. But if pi is in the denominator, we can't just let it move up to the top. That's a different number. Okay, so it cleans up all the way to 9/10 with a pi in the denominator. And what's our unit of measure here? Height is in terms of feet, time is, so feet, per minute, right? Okay, so feet per minute. Yeah, 9/10. Did you not get that? Yeah, it should reduce. Yeah, it should reduce there to 9/10. Right, any questions here? Now, let me add on to this problem. What if it says find the rate of change of the radius of the water? Yeah. At the same moment, okay? Let's say this is part B. Find the rate of change of radius of water. Now, we could, okay, we don't want to do this, but we could replace everything in terms of R and then go through this process again. But there's a quick and easy way for us to get from DHDT to DRDT without having to go through the whole process. And we have another equation that relates R and H. We can just use that, right? What equation did we build earlier? Yep, so there's our relationship there. So what I meant before was if you decide to solve for R and you realize you solved for the wrong rate, you can simply rely on this to just take you back to whatever you're looking for. So it's not, it's just one additional step, so it's not too bad. But I want to kind of show you, if I want to find DRDT from DHDT, let's find the derivative. Let's use the space for number 4 since we're not going to do number 4. So if I have 12R equals 5H, what's the derivative of this simple equation here? 12R becomes CR. Yeah. And 5H becomes 5DHDT. So if I know what DHDT is, just put that in and I can solve for DRDT. Likewise, if I realize, oh, I thought I was solving for DRDT and it ends up being DHDT, it's still useful. You just take that DRDT, create the derivative from the relationship you built using similar triangles, and then just do one more additional step to convert over. Okay, so here, if I want to do that, 12 DRDT. So it's a nice, easy way to jump back and forth between the rates. There's no need to go back to the original equation and build the volume equation from scratch. Okay, let's just go through a variety of different problems here. There's also another similar right triangle problem that's very specific, but it's shown up on the AP exam, so we want to make sure we go over it. So let's go to page 14. But any questions here? Are we good with similar triangles involving cones? Okay, so this is what we call a shadow problem here. Let me walk through the process here. A man is 6 feet tall. So here's the person here. He's walking away from a lamppost at a rate of 5 feet per minute. So here's the lamppost, 20 feet tall. The person casts a shadow on the ground in front of them. So the light from the lamppost is going to cause a shadow to form here. Okay. How fast is the shadow growing when the person is 30 feet from the lamppost? And then part B, how fast is the tip of the shadow moving when the person is 30 feet from the lamppost? So I want you to kind of visualize what's going on here. So this person moves towards the lamppost. His shadow is going to get smaller and smaller and smaller. Okay, as he moves further and further away from the lamppost, that shadow is going to get longer and longer. Okay. The second thing is that we're going to figure out the rate that the shadow is increasing or changing, but we're also going to have to figure out how fast the tip of the shadow is moving in relation to the ground. Okay. So here are the different rates, and we're going to build this in a second. But first, dx dt is going to represent the rate that the person is walking or changing in relation to the ground. And then dy dt, this is the shadow here, so dy dt will represent the rate of change of the shadow length. But then the tip of the shadow is going to get influenced by how fast y is changing and by how fast the person is walking. So these are two different rates here. So if I want to find the rate of change of the tip of the shadow, I'm going to have to add the rate that the person is walking in addition to how fast the shadow length is increasing. So both are going to influence the tip of the shadow. Okay, so this is how we can start. The way we can start is we're going to create a right triangle relationship here. And I like to always start off with this. So this is always the given. I have my 6, I have 20. I like to go from left to right. So this is x and that's y. All right. So we're going to create similar triangles here. So hopefully we see, let me draw that out so you can kind of see the two triangles in play here. We got the large triangle. And then we have the small triangle, which I'll put in red. Right. We're going to create proportions here. So I can say the height of the small triangle is to the height of the large triangle as the base of the small triangle. What's the base of the small triangle? Y. Y. Is to the base of the large triangle. What's the base of the large triangle? X plus y. X plus y. So I think this is the hardest part, just making sure that we build the relationship correctly. Some students, they want to say x over x plus y, but we can't say x as a full length base of any triangle, right? We want to say y over x plus y. So this is the equation. We're going to find the derivative, but it's a little bit easier to find the derivative if I don't have to deal with a fraction. So I'm going to just cross multiply, get the fractions out of the way, combine some like terms, and I'm going to find the derivative. All right, so we have a nice simple equation, right? It's a lot easier process than with cones. So what's the derivative of 6x?
60 of x.
Good, right? So we're still dealing with related rates here. Time is still influencing every variable. So d over dt will still influence every variable. Okay, 14y becomes 14 dy dt, yeah. Okay. So that's the only calculus step from here to here, right? It's an easy step. Now let's gather some information here. Person is walking away from the lamppost at a rate of 5 feet per minute. What's happening to x? Increasing. So this is going to be dx dt, positive or negative 5? Positive 5. Okay, so dx dt, the positive 5. And I think that's all we need to plug in, right? If I plug in 5 for dx dt, I can find dy dt. If I find dy dt, I found the rate of change of the shadow length. And then if I have dx dt and dy dt, I can just add those together, and that's the rate of change of the tip of the shadow.
I have a question. When would the dx over dt be -5?
If the person is walking towards the lamppost, then x is decreasing, then we got to force that to be a negative. Okay, so we found that the shadow is growing at a rate of 15 over 7 feet per second. And then part B, how fast is the tip of the shadow moving? Add the two rates together.
How is a feet per second?
Oh, per minute. Sorry, thank you. Or per feet per minute. Now, there's something that we never even touched in this from what's given to us. What did we not use?
30 feet.
Yeah, just 30 feet. We never used it because it has no impact, right? Our derivative did not require the distance. It's the rate is constant, so it doesn't matter how far he is away from the lamppost. The rate is going to stay constant. So, yeah. The reason why I include this because this is similar to how the AP exam has it give you some extraneous information that you don't really need. By the way, that's usually not the case. Usually you don't see a whole lot of problems where they give you information that you don't even use, but this is one of those instances. Okay, how do you feel about the process here? I feel like if you can set up the similar triangle relationship correctly, and then if you know what dy dt and dx dt, what they represent, then it's not so bad. But it's very specific, right? It's a very specific process for a very specific problem. Okay, you guys want to try number 2 and see if we can feel comfortable about this, and we can move forward from here. So try number 2. You're going to set up the diagram the same way. Your heights, and then your x and your y. Slight adjustment here. The man is walking towards the pole. How's that going to affect the rate? Negative, right? Not because he's going left, but because that distance between him and the pole is decreasing. That's why we want that rate to be negative. Part A is switched around here. Part A is asking for the tip of the shadow. So we got to add the two rays together. dx dt and dy dt gives us negative 7.5. But then part B is just the length of the shadow changing. That's just dy dt. That's negative 5/2.
Instead of cone problem, we have a cylinder problem, so then only the height would be changing. How'd that work?
Yeah, that's the next problem that we're going to do. Yeah, so I do want to distinguish between cones and cylinders, and cylinders are a lot easier than cones, but a lot of times we don't think it is because the formula looks so similar to each other. Yeah, but we're going to explore that next. Okay. Any questions with this very specific type of shadow problem here? Okay, we're going to do number 4 next on page 15. Okay, are we good here? Anybody still need this page? Okay, so we talked about cones. This is on page 15. We talked about cones and how we got to go through a similar triangle because radius and height are both changing, and there's too many variables, and we want to get one in terms of the other. Okay. So I want to talk about cylinders here. Okay, guys. Okay, so let me talk about cylinders here. What's different about cylinders is I want you to imagine the water level rising and falling, okay? Obviously, the height is changing. But what about the radius?
Constant.
Staying a constant. So it's easy to get these two confused because if you look at the formulas, they look virtually the same. But related rates wise, this is a lot easier because there's no need for us to hold on to that radius variable. That radius is staying the same, right? The water level could be empty, it could be near the top. That radius is holding constant. So what that means, we can get rid of the radius to begin with at the beginning of the problem, and there's no need to go through similar triangles. I think, some students, they force similar triangles into this problem. There's no triangle for us to deal with here, right? So I want us to make sure that we understand cones. We got to go through that full process, but cylinders, different process, but a lot easier. Okay. Let's read the problem here. It says a coffee pot has the shape of a cylinder with a radius of 5 inches. So radius is 5. Let H be the depth of the coffee in the pot, measured in inches, where H is the function of time t, measured in seconds. The volume of the coffee is changing at a rate of -5 pi root h cubic feet inches per second. Find dH dt as a function of h. This means your answer will contain the variable h. All right, so let's gather some information here. We know that radius is 5 inches. Now, if you know your radius is 5 and it's not changing, there's no need to hold on to that r variable. Let's go ahead and replace it. Right, it'll simplify our equation immensely. Okay, so this can be our starting equation, right? No need to do, small radius or big radius equals small height over big height. We just go ahead and replace the radius. Okay, let's get the derivative out of the way. Okay, v becomes what? 25 pi h becomes what?
25 pi h dh.
Good. 25 pi is constant. There's no need for product rule there. That's just a number that's going to hang out in front. And then h becomes dh. Okay, so what information do we have? It says the volume is changing at a rate of -5 pi root h. What do we assign that to? dv dt. Find dH dt. Okay, so it's one substitution, divide, and we have our answer, right? So I want you to recognize that cylinders are a lot easier and not to overcomplicate it by forcing a cone problem into a cylinder.
Is it? Wait, oh, no.
Yeah, the dv dt is just -5.
Yeah, okay.
Okay, so we have our answer. They did not tell us what h is, so we have to leave our answer in terms of h. What's our unit of measure? Height over time. What's the height? Inches, yeah, inches and seconds. Okay, page 16. I want us to do an old FRQ problem together here. Okay, a circle is inscribed in the square as shown in the figure. The circumference of a circle is increasing at a rate of 6 inches per minute. As the circle expands, the square expands to contain the condition of tangency. So as the circle expands, the square is still going to grow with it and it's still going to maintain that tangency with the circle. Okay. Circle has radius r, circumference c equals 2 pi r, and a equals pi r squared. So it's given to you right now, but I just want to let you know, on the test, I expect you to know these two. Okay, and I'll tell you exactly what I want you to know and what I'm going to give you on the test. But circumference and area, I expect you guys to know, to memorize. Okay, it says find the rate at which the perimeter of the square is increasing. Indicate the units of measure. So perimeter of a square, what I want us to do is we're only given radius r, right? This is the only variable here. We're going to try to define everything in terms of this variable, right? So we don't introduce a different variable here. We're going to just think in terms of r here. Now, if I want to create the dimension of the square, what can I say about dimensions of the square?
It's 2D.
2r, right? So we want to minimize the number of variables involved, right? If we start involving x or calling it a different variable, then we lose that connection with what we have here. Okay. Before we can find the rate at which perimeter is increasing, let's first build the perimeter, right? Let's build the perimeter equation. What's the perimeter of the square?
8r.
8r, right? 2r plus 2r plus 2r plus 2r. So before we do anything with related rates, we're always building some sort of a geometric or algebraic equation to start with, and then we can build the derivative. Okay, let's find the derivative now. P becomes 8r becomes
8dr.
Yeah. So let's just gather information and plug in. All right, circumference of the circle is increasing at a constant rate of 6 inches per minute. So I'm going to put this to the side. I don't know if I'm going to need it or not. That's my dc dt. Okay, so I'm trying to find drdt, but I only have dc dt. So maybe there's another relationship I can create, right? Well, I know my circumference is 2 pi r. Yeah, let's find the derivative, right? If I can find the derivative here, then that will help me lead to what I'm really after, which is drdt. So dc dt is 6. That will help me get to drdt, and then that will help me get to what I'm eventually looking for with dp dt. Okay, careful. In this case, the pi is also in the denominator. It needs to stay in the denominator. Okay, now I have what I'm looking for, right? I can make a substitution there. drdt is 3 over pi. Put that in here, and that can get me the dp dt. Okay, perimeter is a one-dimensional unit, just going to be inches. Time is minutes, so inches per minute. Okay, we'll finish part B tomorrow. There's one more thing that I haven't done with related rates, and that is with trig. I know it's shown up in your homework, but I'll do a full list. Well, I'll go over that fully with you, and then we can also begin indeterminate form and L'Hopital's rule. Yes.
Can you post or like,
Yeah, I guess it's not up there yet, so I'll go ahead and try to do
I
that.
did that one.
Okay. All right, go get your phones.
Like,